Last time we looked at those three numbers, how many standard deviations we need to go out from the mean in order to catch a particular percent of the population. Let's look at a couple applications. Go back to IQs, not because they're important, because the numbers are easy. We know IQs are normally distributed with a mean of 100 and a standard deviation of 15. So suppose I wanted to capture 95% of the population between two IQ scores. I want to say everybody between this IQ and that IQ, and that would constitute 95% of the population. Well, let's take a look. We know we're going to go down some distance from the mean and up from the mean. So we start with 100, go down, go up. And we looked at last time, in order to catch 95%, we needed to go 1.96 standard deviations up and down from the mean. So if we do 1.96 times 15, that tells us how far we have to go. We subtract that, we'll get our lower score. And if we add 1.96 times 15, we'll get our upper score. Okay? That's just calculator work. 100 minus 1.96 times 15, and we get 70.6. And if we go back, remember, if you hit second entry, you get your original calculation back, and you can just change that to a plus instead of having to type all the numbers in again. And we get 129.4. Okay, so 95% of the populations have IQs between 70.6 and 129.4. Suppose we wanted to get 99%. Right? We want 99% of the population. The number for that was 2.58. We need to go out 2.58 standard deviations from the mean. And that's the only part that changes, is how many standard deviations. The mean's the same, the standard deviation's the same. We just need to go out farther. So we need to go 2.58 standard deviations from the mean. And that's going to give us some slightly different numbers. We'll go 100 minus 2.58 times 15 for our standard deviation. That gives us 61.3. And same thing, but with a plus, will give us 138.7. Looks like I'm losing some pixels on my calculator. Good. After 25 years of teaching, I can finally buy a new calculator. All right. I hope this is making sense. Let's do one more. Let's talk about commute times. Suppose we've got commute. Suppose our average Jefferson College student has a commute time of 25 minutes. So a mean of 25, right? Mu for the mean. And then standard deviation, sigma, of 10. Standard deviation of 10 minutes for that distribution. And suppose, since we haven't done a 90% yet, we want to capture that middle 90% of commute times. Well, we know that's going to be 25 plus and 25 minus, sorry, different order this time. The z-score associated with 90% was 1.64. So we do 1.64 times the standard deviation, 1.64 times the standard deviation. This is very much like finding that expected range of outcomes that we talked about in the previous unit here. 1.64 times 10, and that gives us an upper time of 41 minutes. 41.4. That's horrible. I apologize for my lousy writing. It's much better on the board. And 8.6. So we'd say 90% of Jeffco students have a commute time between 8.6 minutes and 41.4 minutes. Now let me give you one. Suppose height of pine trees. Heights of pine trees average 75 feet with a standard deviation of 12. Find the range for 95%. Now pause it and do out the work. I'll give you the answer here, but do it yourself and check after. Okay? You should get between 51.48 and 98.52. All right? If so, good. If not, go back and figure out what you did wrong. Suppose we've got foot-long subs. We're going to talk about those a lot this chapter, and we've talked about them in class also. Suppose that foot-long subs at Subway average 12.2 inches with a standard deviation of 0.2 inches. Find the range that captures 99% of the foot-long subs. Again, pause it. You should get between 11.684 and 12.716. If not, go back and figure out where your problem is. I will see you next time.